Mapping an algorithm's maximum execution time gives us a useful safety margin. It tells us exactly how bad things can get. But capping the worst-case scenario only tells half the story of its true efficiency. To fully map out how software behaves, we have to flip our perspective. We need to pivot away from finding the upper limit and establish a mathematically proven minimum growth rate. Think about a long train journey. If weather and track conditions are terrible, the trip might take a maximum of 8 hours. But the laws of physics dictate that even under completely perfect conditions, no traffic, maximum speed, the train can never arrive in less than 5 hours. That 5-hour mark is an unbreakable floor. No matter how much you optimize the conditions, the total time will never drop below that lower bound. In computer science, we formalize this lower bound using omega notation, represented by the Greek letter omega. Where big O defines the strict worst-case scenario, omega rigorously defines the absolute best-case scenario. It answers a simple question. At least how much time will this algorithm take? Returning to our train analogy, we can plot these limits. Big O captures the 8-hour maximum at the ceiling, while omega captures that 5-hour minimum at the floor. When we plot this graphically on a Cartesian plane, our algorithm's actual performance curve, f of n, will fluctuate based on the data, but it will always remain strictly above the supporting mathematical boundary curve of omega. Defining this floor provides the missing half of the performance profile. It gives us a formal way to calculate the minimum time required when input data is perfectly arranged. Moving from a conceptual graph to a verifiable proof requires a strict mathematical framework. This is the formal definition. A function f of n belongs to the omega class of g of n only if it meets a strict inequality condition. The variable c acts as a constant multiplier and must be greater than 0. We also define a starting parameter, n0. This mathematical floor is only guaranteed to hold true for data inputs that are larger than this specific starting threshold. Focusing strictly on the inequality symbol reveals how the mathematical logic shifts. When we contrast the omega inequality on the right directly with our previously learned big O inequality on the left, their inverse relationship becomes explicit. The less than or equal to symbol of big O bounds a function from above. It presses down, creating a ceiling. But omega relies on a greater than or equal to symbol. It pushes up from below, creating a supporting floor. Reversing that single symbol shifts our objective entirely. We move from mapping worst-case processing maximums to mathematically locking in best-case operational minimums. Let's test this framework with a practical proof. How do we guarantee minimum operations for a linear time equation, like f of n equals 3n plus 5? Our objective is straightforward. Find a positive constant c that makes 3n plus 5 consistently greater than or equal to c times n. Look at the left side. Because our input n represents a positive amount of data, adding the constant 5 ensures the total value will always be larger than 3n operating alone. Because 3n plus 5 is greater than or equal to 3n, we can cleanly select 3 as our necessary constant. The proof holds. This linear function officially establishes a lower bound of omega n. We can apply the same logic to a more complex quadratic curve. Take f of n equals 4n squared plus 2n plus 1. To find our floor, we direct our attention to the lower order terms at the end of the expression. The input size n is always a positive integer. Therefore, the grouped value of 2n plus 1 will always be strictly greater than 0. Stripping away positive lower order terms mathematically guarantees that the remaining isolated expression is smaller than or equal to the original equation. With the expression isolated to 4n squared, we identify our constant multiplier directly from the highest order term. C equals 4. The proof is complete, formally assigning this quadratic function to the omega n squared complexity class. Algebraic deduction proves positive lower order terms add weight to a function. By stripping them away, we isolate the highest order term, revealing the absolute mathematical floor.
Software engineers rarely write out long-form algebraic derivations while writing software. They rely on shortcuts. Finding an omega class boils down to 3 rules: remove constants, keep the highest mathematical power, and ignore lower-order terms. Applying this to 5n plus 10 strips the 5 and 10, leaving the core omega of n class. We can map these mathematical rules directly onto structural code analysis, starting with a basic variable assignment. A singular instruction executes in a fixed time frame. It requires one discrete operation, establishing an omega of 1 complexity. Moving to an iterative structure, we introduce a standard single for loop designed to execute from 1 to n. Regardless of internal conditions, that loop structure is bound to iterate at least n times. The algorithm's linear lower bound is omega of n. Wrapping that same iteration inside a secondary sequence creates a nested for loop scenario. Nested iterations multiply the minimum operation counts together. This ensures that the execution time scales quadratically at an absolute minimum. These 3 rules allow developers to glance at an algorithm's blueprints and deduce its inescapable performance penalty without running a single line of code. Real-world data doesn't sit neatly at the top or bottom of our charts. Let's look at a functional software pattern where the best and worst-case execution times diverge. A standard linear search algorithm scans sequentially through an array until it finds a target key. In the best-case scenario, the algorithm searches for a key that happens to be sitting right in the first index position. Because this search terminates after a single step, its minimum time complexity is strictly constant, omega of 1. Contrast that with the worst-case scenario. The target key is buried at the extreme end of the array, or missing completely. Missing the target early forces the search to continue n times, establishing a linear ceiling, O of n. Depending on the shape of the data, the actual running time of our software will fluctuate between these 2 mathematical constraints. Omega acts as the absolute structural floor of the algorithm. Big O serves as the structural ceiling. The true execution reality is constrained within the gap between them. But this leaves us with a critical theoretical question. What happens to our performance guarantees when that gap closes? When the floor and the ceiling converge to the same mathematical value, we establish theta notation, the tight bound.